Welcome to our last video in chapter 12. Finally, we made it. This last video is going to have to do with graphing. So we are going to start with graphing cylinders, and I don't mean that the cylinder you saw back in geometry, and then what's called quadric surfaces. So this is our last objective. Definition, first we're going to start with a cylinder. A cylinder is a surface that consists of all lines parallel to a given line and passing through a given plane curve. Okay, so what that means in simpler vocabulary is that in 3-space the equation only has 2 variables. So we looked at this a little bit in the first video, I believe. So if we look at example 1, we are sketching z equals x squared in 3-space. So what I always suggest is that you start by sketching the graph in 2-space. So in this case, we're going to look at the xz plane. So when we do this, we just get a typical parabola. So that would be our curve. Now, because there's no y, what that means is y doesn't matter. We're going to have this same parabola for every value of y. So if we have our x, y, and z, this is not going to be the prettiest figure, but if you can picture, we have this xy parabola that is running parallel or along this y-axis. Like I said, not great. It's not a pretty picture. What I was looking for is it's almost like you took a piece of paper and you rounded it the long way. That's what we're looking for along the y-axis. Let's try another one and see if my drawing gets any better in example 2. So in example 2, we are sketching y squared plus z squared equals 1 in 3-space. So again, I would suggest that you start in 2-space. So if we do this as y versus z, or you can flip them, it doesn't matter, you're going to get a circle that has a radius of 1. Okay, so what that means in 3-space then is no matter the value of x, we're always going to have this circle with radius of 1. So we have our x, y, z. Again, ignoring x for a minute, when x is 0, we get this circle of radius 1 that is going to continue all the way down the x-axis regardless of what x is. And it's going to continue back as well. So this is the typical cylinder that you would expect to see. Okay, so that's a cylinder. In general, both examples 1 and 2 were cylinders. What is new that we're going to talk about today is a quadric surface. So a quadric surface is the graph of a second-degree equation in 3 variables. Okay, you don't need to pay attention to that whole long equation. What matters is second degree, and it has 3 variables. So you see example 3, second degree, it has x squared plus y squared, and it's in 3 variables. Okay, in general, we're going to talk about this one and some ways to kind of think about it, and then we're going to look at the different shapes you could have. So the first thing that I want us to notice is because z is equal to x squared plus y squared, z is always going to be positive, or 0 or positive. There's no way for z to be negative. If we plug in some values of z, like z equals 0, we get 0 equals x squared plus y squared, which is a point. All right, that's the point 0, 0, 0. So what we know so far, if we go to graph this, so there's no negative z values, and we have a point 0, 0, 0. If z is 1, the equation becomes 1 equals x squared plus y squared. So when z is 1, we get a circle of radius 1. If we pick another convenient value, 2 is not convenient. If I pick 4, I get 4 is equal to x squared plus y squared. So when z is 4, I have a circle of radius 2. And hopefully we can see that's going to keep going no matter what the z value is. So we get something that comes up like this, almost like a 3D parabola. So that is our figure, and of course it keeps going. So what we did there, what these were that we found when we chose a specific value for z, these are called traces. These are called traces. And so what we're going to look at in a minute is there are 6 different quadric surfaces. We're going to look at the general shapes, what their traces look like, and then from there we're going to do a few examples. Okay, so getting into the general shapes. The first general shape that's based on the equations is if you have x, y, and z all squared, all adding together equaling to 1. That's what we call an ellipsoid. Before we look into a picture, I want to talk about what the intercepts and traces look like. We're going to look at all the intercepts. So if we plug in 0 and 0 for y, we're going to get plus or minus c. If we plug in 0 for x and 0 for z, we're going to get plus or minus b. And then we'll get plus or minus a. Okay, for the traces. So if I make x some number and I leave y and z, y squared over b squared plus z squared over c squared is an ellipse. So any of the 3 traces, if we make x a number, y a number, or z a number, any of those are going to give us ellipses. Okay, so then the question is, what does this actually look like for us? So in this case, x, y, and z can be negative, so I'm going to keep these going. For z, we're going to have a positive c and a negative c. And then for x, we're going to have an a and a negative a. And then for y, we'll have b and negative b. And if we make x a certain value then, for c, we're going to get an ellipse. If we make y a certain value, we're going to get an ellipse. And so on and so forth. So this is not the best ellipse that I've ever drawn. But if we connect all of our dots, we get what is called an ellipsoid. An ellipsoid. So it's kind of like a football shape. Again, I know we can't picture it necessarily because my figures are so poor, but hopefully you get the idea. Let's talk about the next one. Next one is a cone. Okay, in the equation that I have written, we have z squared over c squared is equal to x squared over a squared plus y squared over b squared. This is not always going to be z. That could be x or it could be y. But what that tells us is our axis, the axis that the cone is going along. Okay, so first thing to note is there's only one intercept, and that intercept is 0, 0, 0. That's it. Next thing to notice is for your traces. If z is equal to some number, that's going to give us an ellipse. But if x or y are equal to some number, this is a throwback to conics, but if x or y are equal to some number, we're going to get a hyperbola. Okay, so here's what this gives us then. I'm not going to go in detail through every single problem, but our only intercept is at 0. We're going through the z-axis or along the z-axis. So there would be our equation. And again, this is only going through the z-axis because we have z equals, or z squared equals. Okay, the next one, almost the exact same equation, except this time z is not squared. Again, that might be switched out for x or y. This tells us the axis again. So let's take a look at our only intercept, again, is 0, 0, 0. And for our traces, if z is equal to some number, again, we get an ellipse. This time, though, if x or y are equal to some number, so if x is equal to some number, let's say, then all we have is y squared. These would give us parabolas. And one thing to remember, in this case, z is only 0 or bigger. So what this is going to give us then is something similar to that example 3 we did. Okay, so those are the first 3. And then we've got 2 more or 3 more general shapes before we get into some examples. Okay, next one is called a hyperboloid of one sheet. So what you're going to notice is it has the x squared, y squared, and z squared again, similar to an ellipsoid, but it does have the negative. And again, any of the variables could be negative. This tells us the axis. So this hyperboloid of one sheet is going to be along our axis. Okay, so for any of these ones that we're looking at now, you're going to have to find the intercepts. So we're just going to look at the traces. So I'm going to say find or calculate. Okay, for the traces, x is equal to some number, y is equal to some number, or z is equal to some number. Z is equal to some number, again, is going to give us an ellipse. And again, x and y are going to give us hyperbolas. Okay, so what's happening here something like this. So that is called a hyperboloid of one sheet. And again, it's running parallel to the z-axis because of that negative z. Next one is a hyperboloid of 2 sheets. This time z is the different one because it's positive. Again, that's going to be the axis. Looking at our traces. If z is equal to some number, again, we get an ellipse. This time, though, z has to be bigger than c. X and y are going to give us hyperbolas. So what this one gives us when we go to graph something like that. So that is our hyperboloid of 2 sheets. And I know I'm going through these quickly, but we're going to do some examples where we see how to actually use this. So then last one is called a hyperbolic paraboloid. Hyperbolic paraboloid. So looking at traces, x and y equal to some number give us a parabola. Z is equal to some number gives us a hyperbola. Okay, I'm going to tell you right now, this is the hardest one for me to draw, so don't have super high expectations. Okay, hyperbolic paraboloid. Again, if my drawings are so bad that you can't understand them, please look in the book. But it's supposed to look like a saddle, like the saddle you would put on a horse. That is a hyperbolic paraboloid. Okay, so you might be thinking or asking yourself right now, How the heck is she going to grade this? I'm not an artist. Of course you're not an artist. This is not an art class. You need to be able to show the work for finding these and do the best job you can graphing. So let's take a look at a few examples so we know the techniques. I am not asking you or telling you to memorize these formulas. But it is important that we have a basic understanding of what these look like, because moving forward in Calculus 3, knowledge of what the figure looks like is going to be incredibly important for setting up integrals. So let's take a look at some examples. Here's the first one. Y squared equals x squared plus z squared over 4. Do not memorize this. Don't look back at the table. Instead, let's start by finding intercepts. There's only one in this case, 0, 0, 0. And then let's look at some traces. Because it's y squared equals, we can probably guess that y is going to be our axis. So I would choose some values for y. If y is equal to 0, it gives us 0 equals x squared plus z squared over 4, which again is just that point 0, 0, 0. If y is equal to 1, 1 is equal to x squared plus z squared over 4. If y is equal to 2, we're going to get 4 is equal to x squared plus z squared over 4, which we often wrote as x squared over 4 plus z squared over 16. So hopefully we can see all of these are giving us ellipses. Okay, so then it might be a little bit helpful if we were to try some values of x or y. So if I choose x equals 0, I'm going to get y squared is equal to z squared over 4. So plus or minus y is equal to plus or minus z over 2, which is going to give us a cross of some type. So x is equal to other numbers, again, going to be a similar idea. Okay, so then the question is, having all of this information, where does that take us? We know we're going along the x-axis, that is our axis. We know that we have an intercept at 0. We know we have these cross lines or really planes at y equals z over 2. So we're going to have something that goes up like this and then comes back down. Similar thing here. And then we also know that we have these ellipses. So these ellipses that go along the y-axis. Something like this. So what we see is our figure looks something like this. It's an elliptic cone. Elliptic cone. I didn't do it on this one, but I will on the next one. I would really appreciate if you tried your best to do scaling of some type when you can. Scaling of some type when you can. So let's take a look at this example 5. This one is a little bit tougher because it's not in a nice, friendly standard form. So we're going to need to start by doing that. I'm going to move my x's together, my y's together, my z's together. So I have 4x squared plus 4. Hopefully you see that you're going to have to complete the square. So we went over this already in a previous video. Take the middle term, divide by 2, and square it. Now, because I factored out this 4 is really what I need to add. So take that middle term, divide it by 2, and square it. So where this gets us is we have 4x squared, add 4 times y plus 1 squared, add z subtract 2 squared is equal to 4. Divide everything by 4, so we get x squared, add y plus 1 squared, add z subtract 2 squared over 4 is equal to 1. Is equal to 1. Okay, so now let's talk about some intercepts. If we make x 0 and y 0, z is going to be 2. If we make x 0 and z 0, y is going to be negative 1. And if we make y 0 and z 0, then what I see is that's not possible. I would have x squared, add 1 squared, add 1 is equal to 1. That's not true. X squared equals negative 1. So we're going to say there are no x-intercepts. And the other point that hopefully you can see from the way this is set up is the point 0, negative 1, 2. While that's not on the graph, it's the center of what we're doing. So now, if we imagine making x, y, or z any numbers at all that we want, looking at our traces, hopefully we can see they are all ellipses. They are all ellipses. Okay, so if we graph this, what are we looking at then? So let's graph some points. We have our 0, negative 1, 2. So negative 1, 2. We have 0, negative 1, 0, which is here. We have 0, 0, 2, which is here. So what we're looking at is this ellipse right here. And to give it a little bit of perspective, so this is our ellipsoid. Okay, and then we have one more to graph. And it's this last one. Okay, starting with intercepts. If we make x 0 and y 0, we get z to be 0. If we make x 0 and z 0, we get y to be 0. So hopefully we see that's really our only intercept. And for our traces, x is equal to some number, y is equal to some number, and z is equal to some number. All of them, the first two rather, give us parabolas. And then we have a hyperbola. So we get a hyperbolic paraboloid, aka the graph that looks like a saddle. Our only intercept is at 0, 0, 0. And then we're going to get these parabolas, not parabolas, hyperbolas. And there we go. There's our hyperbolic paraboloid. Okay, so again, I want to emphasize we are not memorizing. We are not memorizing these equations. Instead, we are taking a look at the traces, the intercepts, and what should be going on in each plane. Okay, if you were going through this video thinking, oh my gosh, I really need to review conic sections like hyperbolas, parabolas, ellipses, you're not alone. I'm sure a lot of people do. So I will put a resource on Schoology, and I will also link it at the bottom of this video so that you can review those on your own if you need to. Good luck and congrats on finishing Chapter 12, Geometry and the Vectors of Space.